Hey everyone, thank you for coming. My name is Steinbrecher. I'm an engineer at Meta. This is Surendra. He's an engineer at Broadcom. We're going to be talking today about some work we did together on microsecond flow-aware congestion measurement of real-world traffic at scale, which you can read on the screen. This is work we've done over the past couple of years, developing novel measurement tooling as a collaboration between Broadcom and Meta. We're going to talk both about the measurement tooling itself. I'll talk a little bit first about the motivation for it, and then share with you some real-world data and how we've used that data. So, wanted to frame this around the motivating problem that we cared about, which is that, as many of you are probably aware, switch power has been growing generation over generation. So, data centers have limited cooling power available to them, and a lot of them have non-fungible power. So there's dedicated cooling and power available for network hardware that is separate from the power for compute. And so that puts a strong, hard envelope on the amount of power that you can spend on your switching hardware in any generation. Even in data centers that are designed to have fungible power domains, power that you spend on the network can't be used for compute. And so since compute is what runs our applications, we obviously want to allocate as much power for that as possible, given the constraints of how much power we need for the network. And of course, applications do benefit from bandwidth growth, so we can't just keep our network in one generation over time. We need to keep upgrading it to keep our customers happy. Customers here being application teams. So one theory that we had for how to reduce power in future generations was to reduce the packet per second capability of the network switch. So switch ASIC power is divided into 3 domains. There's the I/O limited power domain. This is things like your SerDes. There's the BPS limited. This is purely the ability to push bytes per second through the switch. So this is your memory and buffering, et cetera. And then there's PPS limited, which is the work you have to do on a per packet basis as opposed to on a per byte basis. And switches historically have designed for the worst case packet rate. So an Ethernet switch, your frames might be as small as 64 bytes. So you take your line rate, you divide it by 64 bytes, that gives you a worst case packet rate. And historically, that was the packet rate that switch designers targeted. This hasn't been possible in several generations of network switches. The I/O has gotten too fast, and so the kind of average supported packet rate in terms of streaming packet rate over time, if you just plug this thing into an Ixia or other traffic generator on all ports, and you run packets through it at 64 bytes at line rate, you will drop packets. So in modern switches, the smallest packet size that they can support really streaming at line rate like that is about 250 bytes. Depends on the specific switch. Some switches do more or less, but that's the regime we're in currently. But that's mostly an optimization, right? Switch vendors are trying to deliver the best they can on that metric. But the question we had is, does this actually matter? Do we actually need streaming packets at an average size of 250 bytes? Or could we get away with less and use less power driving all of that packet switching transistors? Unfortunately, the timescales that are relevant to answering this question are in the microseconds, not in the minutes, where we typically find monitoring. So existing monitoring tooling for us typically gives minute scale resolution. So to the left, we have data from Meta's data center networks at different tiers of the network, sampled at 100 gigabit per second ports. So 1 in every 10 million rack switch ports will continuously serve 15 million packets per second or more. It's even lower at higher tiers of the network. 15 megapackets per second is an 833 byte average packet size at that line rate. And so that's significantly above the 250 that we're targeting. But the problem with this is minute scale. And so switches have buffering built into them to absorb bursts of smaller packets, but those buffers can fill on the microsecond time scale, not on the minute time scale. And so we really need monitoring available to us at much shorter time scales to be able to understand if it would be safe for us to reduce the packet processing capabilities of switches or if we would be losing traffic as a result.
Thank you, Greg. I think that's an excellent motivation presented. So this is a problem that we started with, saying, okay, can we measure the queue congestion and the packet rates and the flow data that's going to the switch at something that's much finer than minutes? Not even seconds is sufficient, even milliseconds doesn't cut it. You need to get to microsecond level, as Greg is putting up. The reason is, when you average over a minute or a second or even a millisecond, it may appear as if there is a lower rate, but at a microsecond intervals, there could be spikes in the traffic, like microburst. And that is related to the switch buffer. So if your switch buffer is in the order of many, many microseconds, which you typically want it to be because of the lower latency that you normally maintain, and you want to be able to measure at that time scales of the switch buffering. So queue congestion monitor is the application that is done, is a feature that's done to address this measurement problem, which is how do we get to a microsecond level granularity. So queue congestion monitor is a collection of building blocks that are available in the modern switches, like Tomahawk switches and the class of products, is that there's, the first one is a buffer statistics tracking, which is there's a event-driven buffer statistics tracking, where with every time a queue reaches a congestion level, you could generate an event, and that event can capture at a fine granularity when that event happened, what is the timestamp, what queue, and what is the buffer usage that's happening at the time. And also, this one you can tie it to the flow, saying, okay, what flow is generating this? Is this a elephant flow, mice flow, and what is the start time, what is the end time, what is the flow time? There's a lot of granularity available in terms of reporting. Not all of that is used for the power itself, but that is one of the building blocks that is available. And this one can go down to nanoseconds, not even microseconds, because this is a hardware mechanism which is monitoring the resources on the switch, and that and it can generate the events, and it can buffer it up, and then you can process that. The next one is, okay, now you have events and you're tracking all these statistics at nanoseconds level. Then what are the ones that are interesting? Like how do you weigh these signals? And there's other flexible trigger and reporting framework that is available in the switches, that where you can define metrics or weights that says what the weights will be based on what is the duration of the congestion, various number of items, right? Like it could be based on the switch utilization, packet drops. You could programmatically you can say, okay, I want to look at the events of interest, and here's the definition of event of interest. And if that weightage is multiplied with summed weightage is greater than some threshold, then we can say, okay, this is an interesting signal, let's capture it and let's analyze it further, okay? So, and this mechanism is important because like when you're tracking something at nanosecond level, there could be large amount of data that you want to pick, what you're interested in. Okay, so the next one is it ties these things together, is that when the packets are coming in, they're ingress into the switch, and then we check some of the packets, and then say that we have the flow counters for every flow, and then there's a flow table that will actually be able to capture elephant flows and say, okay, here is the amount of bandwidth that's being used. And also there are counters, what we call flow counters or flex counters, which also count all the packets that are going in. So we'll be able to see what is the total amount of traffic, what queue is seeing that, and what flows are going into which queue, and these things are done. And then on the die, there's an on-die processor, is a real-time processor that actually is used for the export. So one is, of course, you want to be able to capture it, you want to be able to filter it. These things happen at the hardware. And the third one is you want to be able to export it also at a high rate. So it's not enough that you export in a minute granularity. So there's a on-die processor that's working on the real-time OS that uses the IPFix to export these events. So I'm just recapping like what you heard earlier from Greg, which is that switch power is like there's a base load, which is basically like I/O and the quiescent power that you have. and there's a byte processing, like the more bytes that are coming through, the more power that you're consuming, and there's a packet processing, right? So what you would see is that there's a max packet rate that you want to be able to handle versus the average packet rate that you see. With the instrumentation that you're getting here, you will be able to, you have a choice of deciding, okay, hey, I'm not, even at microsecond granularity, here's the packet rate that I'm seeing, so here's the likely packet processing rate that you'll need. And that way you can set the max packet processing rate, and that could result in significant power savings. And it is significant because, like, you can think of these three components. Like, I'm not saying they're equal, but they're roughly there. So if you say that, okay, I don't need to process the packets at, let's say, 200 bytes instead, like, let's say the average packet size that Greg is saying in their workload is twice that, then you would see significant power savings coming from that.
Thanks, Surendra. So that was a great summary of kind of what QCM is capable of, and I wanted to give probably a quick rundown of how we used it to actually solve this problem and understand packet rates in the data center. So we deployed QCM in Meta's data centers. We did this in a limited fashion because this was kind of a high-touch deployment. So we identified the highest impact rack switches that we could do this at. We chose rack switches because the traffic is least multiplexed there, so you don't get the benefit of kind of averaging out over different traffic profiles. We could isolate racks that we knew had kind of the worst case traffic, so highest packet rates with the smallest packets. Particularly, this ends up being cache applications, where there's, because if you think about TCP, it's going to coalesce data if you're kind of moving a lot of it on one connection. And so what you need is an application that serves a very small amount of data to a very large number of other servers on different connections. And cache happens to be the application that is kind of matches that most closely. So we collected several months worth of QCM data, about 20 billion samples from QCM overall. And what we quickly saw was what you can see on the left-hand side here is the y-axis is rate and the x-axis is average packet size over a 4 microsecond window or so. And so what we saw was that we don't actually even hit line rate until an average packet size of 800 bytes, even with this very, very fine-grained resolution. So one of the benefits, I think we haven't specifically highlighted of QCM, but QCM outputs a time series. It's not taking single kind of snapshots and exporting them. It's capturing time series and then exporting them as a full coherent window in time. And so what that lets us do is it lets us concatenate samples together to create kind of a variable windows in time that we're looking at. And so here, this is, we took the same plot as the previous slide, but we drew the 6 nines contour at different averaging times. And what we see is that, you know, as you increase the averaging time, the rate at which you have to, the average packet size you need to hit full line rate increases. So we get bursts of packets at maybe an average packet size of 750 bytes at line rate for maybe 4 microseconds. But even if you're talking about 20, 30 microseconds, those bursts don't last that long. So the utilization is actually like even lower over kind of tens of microsecond scale. And so if we compare this against per minute data, though, we can see the importance of doing these measurements. So that gray dotted line is the 1 minute data that we collected for these switches. But you can see that in the green line, we're observing significantly higher packet rates. But the trend remains the same. So a packet rate over 20 million packets per second is a 1 in a million event. But it corresponds to an average packet size of still about 600 bytes. So significantly above that 250 that switches are designed for currently. So how do we use this to kind of make decisions about what we need to do with switches? And so we wanted to take this data. I'm going to skip kind of quickly over this part. But basically, the data we get out of QCM is packet count and byte count in a small window of time. And we wanted to convert that to pathological packet traces. So if you want to look at the slides later, you can see the details on this. But basically, we collect both the long timescale packet size distribution along with this QCM samples. And we use a rejection sampling process to convert these samples of number of bytes and number of packets into a set of packets. like actual packets on the wire that might have occurred to cause that number of bytes with that number of packets. The way we do this is we just, if you have 31 packets and 35,804 bytes in a sample, you just keep drawing samples of 31 packets from the overall packet size distribution until you get a sample that adds up to the right number of bytes. It's a very stupid but very effective sampling process that gives you a representative sample that could have generated that. So we can use that to then drive a simulation of a switch front end. And so we internally built our own very simplified Verilog model of a switch front end. The person who built it is sitting over there. And used these packet traces to drive it and looked at the utilization of the kind of burst absorption buffers in these actual switches to give us a sense of, if you set a packet clock rate to a given value, how much burst absorption buffer do you actually need? And so doing this type of analysis is really important because we can't just say, what is the average packet size? We really need to understand the hardware level trade-offs that we're making of, okay, we have this many resources allocated for buffer. That gives us this much leeway on how far down we can turn the packet clock and how much power we can save by doing so. And so we varied in the simulations packet clock from 2 nanoseconds to 12 nanoseconds, holding data clock at 1 nanosecond. We made some assumptions about kind of very simple structure of the switch. And what we saw was that even turning the kind of streaming frame size that you can support all the way up to like 1,200 bytes, the amount of buffer you need is still in the tens of kilobytes to support this. So with our traffic, at least, the most stressful traffic we could find, we could turn the packet clock very far down and still push full traffic at as much throughput and not lose any of it. So what we found is there's a significant power savings available to us there. I'll skip over the details of this because we're running short on time. But we've actually deployed this in our data center. So we've reduced the power that our Tomahawk 4 switches use and are deployed in our network by reducing the packet clock rate overall. Tomahawk 4 was not designed with this data in mind, but we were still able to turn the packet clock down, and we were able to realize, without taking advantage of it in the design process, a 13% reduction in max ASIC power overall. And so that allows us to fit significantly more of these switches potentially into our power envelopes that we have that are fixed for network, or in fungible domains, use more of our power for compute. So I think we are out of time, but the quick summary is that understanding your traffic at microsecond timescales in a time-coherent way, so with time series and not just samples, gives you insights that allow you to optimize your hardware. And so, skipping over this, please reach out to me. My email is here. If you're interested in a packet trace data methodology, QCM is available today in Tomahawk. Talk to Broadcom about that. And there's a plan to contribute to OCP Sci for QCM. So, thank you all.